So in this case, the sample is 1.4 mg per mil bovine serum albumin, and we're running it in 100 millimolar KCl, 10 millimolar tris, pH 7.5, a measured conductance of 12.5 millisiemens. You can set up a protocol quite simply. You edit a protocol that has what current you're going to run, what temperature you want to use, what wavelength, how long you want to wait before you take scans. Typically for a mobility measurement, this will be set to 1 second. And how frequently you want to take scans, how many seconds between scans, how many scans total you want to take. And you can take data that are either data where you have protein present, or you can take blank data. Once you're all set, you're ready for data acquisition. Close the cabinet, press start, and I'm going to show you a movie of what you would observe. Now what you see is a boundary moving from left to right. The measurement that's made is the light intensity. So where the protein has gone past, let's go back and take a look at that again. And pause it right here. Where the protein has already gone by, the light intensity coming through is higher than over to the right, where the protein, where the boundary has not passed. We have 512 light intensity measurements across the entire sensor, and approximately 200 to 250 light intensity measurements across the 4 millimeters of the cuvette. Once the data are acquired, then it's time to do the analysis. The analysis typically takes about just a few minutes. What you see with all the scans, these are all 100 scans present. We're only going to use a fraction of the scans for the data analysis. There are some positions we need to know. The most important one is the top membrane. For any of you who have done sedimentation velocity analysis, this is the equivalent of the meniscus position. And your velocity is going to be measured by how far the boundary is moved, divided by the length of time. Each of these scans is roughly 10 seconds apart. And you now see that the boundary is moving away from the top membrane. You always arrange your experiment so the boundary moves from top to bottom. Then there's a bottom membrane position. Knowing this is not quite as important as knowing the top membrane position. And then you select what portion of the image you actually want to use in the analysis, and that's the analysis region. That's defined now by the blue bar and the dark green bar. The top and bottom membrane position are set in over on the hardware side. You can change them when you're doing the analysis, but it isn't always necessary. The next thing you do is pick out which scans you want to use. And so in this case, you can see that we've selected two sets of scans. One of them is the first scan to be used in a data analysis, and that one's now drawn in green. And then the last scan to be used in the data analysis, and that now has been covered with red, so you can see where you're going to stop. At that point, all you have to do is press the Analyze button, and when you do, it takes the first difference between those. And the peak in that is now the peak position in this curve corresponds to the position of the center of the boundary here, corrected not from position to electrophoretic mobility. So if we go back over here, our x-axis is now the electrophoretic mobility, and it's the electrophoretic mobility of those boundaries as it moves down the cell. And the electrophoretic mobility, you can see, comes up with very high precision as -1 × 10⁻⁴ square centimeters per volt second. The precision on this is on the order of a couple of percent. The accuracy for these measurements, we believe, is better than 10%. That's accuracy. The precision is way better than that. Once you have that distribution, you turn around and you can get back the final distribution. So it goes through and determines the average value for each of those curves that it's calculated and gives you back this final distribution. Now we can change this x-axis, and all the changes turn out to be nice, simple, linear changes. We can convert this electrophoretic mobility into charge calculations by entering other data. And these are the Z parameters. There's a tab right there where you can enter them. You have to take into account the solvent conditions, that is the conductance of your solvent, the viscosity, and the ionic strength. And those, you have to measure the conductance. The viscosity and the ionic strength are things that you can calculate once and use again and again and again for a particular solvent. You also need to know the size of the molecules. You need the Stokes radius of the protein or whatever macromolecule you're working with, and you need the counter ion radius to that. Since we usually work in sodium or potassium, we very rarely change the counter ion radius. Stokes radius, though, depends upon the molecule. You can obtain that either from dynamic light scattering or from sedimentation. If we make the conversion now of the electrophoretic mobility to the effective charge on albumin under these conditions is minus 4.1 plus or minus 0.05. If we can also change that x-axis now into the Debye-Huckel-Henry, and the charge that we calculate for albumin under these conditions is about minus 17, between minus 17 and minus 18. When you're done, you can save, when you've done an analysis and you're happy with the analysis you've got, you can save a final report. The program writes this out for you automatically. It's a Word document that you can read into other programs and work with. It saves for you all the parameters that were used in the calculations, your sample description, the solvent description, the various parameters used for the charge calculations. It also saves 3 screenshots, the raw data showing all the data and which scans you selected as the starting and stop, ending scans, the analysis, what kind of analysis was done. In this case, this is Debye-Huckel-Henry charge using 20 scans, averaging 10, and then the final data, the final distribution. These are all written out on the disk, and you can call them into your program. So I want to thank you very much for listening. We'll be glad to answer any questions you might have.